In this video, I'll show you how easy it is to build actively validated services on EigenLayer. Hi, I'm Ed Zinda, and this is What the Funk. This video was made possible by EigenLayer. So first, let's talk about what an actively validated service, or AVS, is. If you go to the EigenLayer docs, I think it does a pretty good job of explaining. So an actively validated service on EigenLayer is a decentralized service built on Ethereum that provides custom validation mechanisms of off-chain operations. An AVS is composed of on-chain contracts for validation and off-chain network operators. Operators execute the service on behalf of the AVS and then post evidence of their execution on-chain to the AVS contracts. So in general, tasks are initiated via on-chain contracts and then off-chain via direct communication with operators. The design of the off-chain execution and on-chain validation is entirely flexible based on the needs of the AVS developer. If operators perform tasks properly, they can get rewards, and if they perform tasks maliciously, the stake that's delegated to them can be slashed by the AVS, or the operator can be removed from the operator set. So if you have a look at the diagram here, you can see that we have an end user or AVS consumer. They would initiate a task via your AVS contract, which we'll build in this video. And we have the operators or operator set. So it could be one operator or a group of operators. And these go ahead and fulfill the task requested by the end user. And they can fulfill this task any way they see fit. They can use whatever language they want, whatever stack they want, whatever infrastructure they want, as long as they follow the rules of the AVS and they're not malicious. And then in turn, as an incentive for completing this task, the operators will get a reward, and the stakers who have delegated stake to these operators will receive a piece of that reward as well. So also on the documentation page, they give a list of all the different types of things you can build as an AVS. So you can do things like MEV services, keeper networks. You can do things like AI inference, manage databases. Basically, whatever you can do off-chain, but verify on-chain, you can build as an AVS. So we're going to build a simple AVS that calls an AI model, and all this AI model does is moderate content. So if you send a string of text to this model, it's going to basically give back a response on whether or not it's safe. So if you look at the README right here, it says Llama Guard 3 has an LLM that generates text in its output that indicates whether a given prompt or response is safe or unsafe. And if unsafe, it also lists the content categories violated. Well, we don't actually care about the content categories violated, and they're listed here. But in this simple AVS example, we're going to be able to request a moderation task on chain, and then an operator on this AVS on their own system is going to run the content against this LLM and then report back whether or not it's safe or unsafe content. I won't go over how to set up Ollama in this video, but it's pretty straightforward. You only need to go to ollama.com, click on the download, and then once you have that set up, you can go ahead and run this command here, Ollama run Llama Guard 3, and we're going to run the 1 billion parameter model because it's very small and very fast. So if you want to do that on your own machine while you follow along on this, you're welcome to go ahead. But I won't be getting into the nitty-gritty of Ollama in this video. Here in my terminal, I'm going to create a new Foundry project. I'm going to call it my AVS. Then a CD into the project. And we're going to install a few dependencies. First, we're going to install the EigenLayer middleware, and we're going to use the mainnet branch because we want to use what's actually deployed on mainnet today as of this video recording. This will take a while, so you might want to grab a cup of coffee. All right, that's done. And the final dependency we're going to install is Solady, which is a very highly optimized utility library for working with smart contracts. And we're just going to do that so we can deal with some stuff later on. So let's install that. All right, and now we're good to go. Now the heart of any AVS is the service manager contract. This is how you will basically register operators to your AVS or deregister, and how you will submit tasks and how operators will submit the results or submit the work of the tasks that they've completed. So this is the main entry point for your Eigen AVS service. So let's go ahead and open that in my editor. At the top, I'll just paste the license identifier. We're going to go with MIT, and then the Solidity version, anything higher than 0.8.26. Next, let's add some dependencies. We're going to pull in the iSignature utils from the EigenLayer contracts. This is actually installed at the same time as the EigenLayer middleware, so we don't actually have to install that ourselves. It's already brought in with that library. We're also going to pull in the iAVS directory. The AVS directory is the entry point for AVSs, and this basically keeps track of which operators are working with which AVSs. And then finally, we're going to pull in ECDSA, and this is a library from Solidity, and this will allow us to work with ECDSA signatures because we're going to have our operators assign different messages, basically registering, deregistering, and for submitting their work when they're running tasks on our AVS. So if you've ever gone into the AVS documentation on EigenLayer, you may have gotten a little bit overwhelmed. There's a lot to go over. There's a lot of moving parts, but really an AVS is pretty simple. You only need about 4 different functions to have a working AVS. You need a way to register your operator to your AVS, deregister, create a task, and respond to a task. Now, there are some other things you're going to want for sure if you deploy an AVS to production. So you're going to want to handle staking, making sure that an operator has enough stake delegated to them. You're going to want to handle ways to submit rewards to different operators and stakers. But that in itself is something that the EigenLayer platform can handle using various different libraries and boilerplate contracts. In this very simple example, I'm just going to go over the fun parts of the AVS. How can you actually go from idea to production and have something working? So we're just going to handle these 4 basic operations, and then I'll go ahead and touch on the things you're going to want to consider on a real AVS later in the video. So first, let's bring in the ECDSA library, and we're going to use ECDSA for bytes 32 values, and this will allow us to easily manipulate signatures and hashes and whatnot. Next, we're going to add a few state variables. Let's go over them one by one. We're going to want to store the address of the AVS directory that's on mainnet, and this will be set when we launch our constructor. Next, we're going to keep track of our tasks. So we're going to have a latest task number so we can increment that every time a new task is created. Finally, we have 3 different mappings. One to keep track of all the operators that are registered to our AVS service. Another mapping to keep track of all the tasks. And another mapping to keep track of all the responses to our tasks. Next, we'll create a few events for keeping track of things happening on chain. We've got a new task created event, and that's going to keep track of the task index and the actual task. And then another event for task responded, and this will keep track of, again, the index, the task, the response, whether the content we're moderating is safe or not, and then the operator that responded to the task. So in order to better handle tasks, we're going to create a type for our task, and it's just going to be a struct with a string for the contents we want to moderate, and then the block that our task is created on. And then here we're going to create a little modifier, which is going to act as a guard for our response function. So we only want registered operators to be able to call that function. So we'll use this modifier for that later. In our constructor, we're going to take in the address of the AVS directory and just set that variable that we defined above. Now we come to the first function in our list of functions. We're going to create a function called register operator to AVS, and this will take the address of our operator, and then the operator is going to sign a signature. Past that signature, it's going to call to the actual AVS directory. The AVS directory will see that this call is coming from our service and will register that operator to our service or our AVS. And then we're also going to keep track of that operator within our service contract as well. So we will set the operator registered for the operator's address to true. And this signature is a struct. We'll have a look at that struct a little bit later. We're going to create a script that makes it easy for an operator to register with our AVS. Next, we add the ability for an operator to deregister, and that's pretty simple as well. So the operator will call this function. We want only an operator to be able to call this, of course. And then we require that the message.sender is actually equal to the operator deregister. We call the AVS directory. We deregister the operator from the AVS, and then we set the operator registered variable or mapping to false. Finally, let's start getting to the fun part of our service. We have a function to create a new task, and all that's going to do is take in a string with the contents that we want to moderate. So imagine you have some sort of decentralized social media service. You're going to want to allow people to post things permissionlessly, but at the same time, maybe on your front end or maybe for your specific offshoot of this service, you're going to want to either moderate things or at least give people the option to view things that may or may not be unsafe to view. So the first step, we will create a new task, set the contents of that task to the contents passed in, and then set the task created block to the block number that it's actually being created on. And then we're going to store the hash of that task in our contract, and then emit a new event with the index of that task. So the very first task is going to be 0, and then we're going to post the full task struct, and then increment the last task number. So any task after that will have the correct index. And then we'll return the new task. So if somebody calls this, they can actually pull this out and save it later. But this event is what's going to be looked at by operators in order to respond to the task. And finally, we have the respond to task function. This will take in a task, the task index, and then the operator is going to run the contents through the AI model, the Llama Guard 3, and determine whether or not the contents are safe. So they're going to set a bool, true or false, whether or not the contents is safe. Then it's going to assign the response, basically showing that, hey, this response came from a valid operator, and we can verify that a little bit down below. So first, we're going to check whether or not the task is valid, whether the task matches the hash that's being passed in. Then we're going to check whether or not the task has already been responded to. Then we will construct the message that the operator should have signed. So in this case, all we want is the result of the LLM call plus the contents of the message that was tested against the LLM, and that's just going to be our hash. And then we're going to convert that to an ETH signed message hash, which basically just prepends the ETH signed message text in front of the message. And then we're going to use the recover method of the ECDSA library and make sure that this was actually signed by the operator that's calling the function. If not, we'll revert. Then we will update the all task responses with the signature that the operator has sent and emit an event saying that this task was responded to, and then the task, the response, whether or not it's safe, and then who actually responded to it. And that's basically it for the smart contract side of the AVS. Next, we're going to create a script that will deploy our service manager locally and also register an operator to EigenLayer as well as our AVS. So let's open that in our editor. Again, we set the license identifier and the pragma. Next, we want to import a few dependencies. First, we have this script library, which is from the Forge standard library, and it's just useful stuff for working with scripts. We import our service manager, which we just created, the delegation manager, the AVS directory, and the iSignature utils, which will be used for signing a message to register to EigenLayer and our AVS. Next, we'll create our deploy script contract in which we want to do some setup, deploy our contract, and then register our operator. So I've pulled the address for the Eigen AVS directory and the delegation manager, and these are the contracts as of today's recording live on mainnet right now. And here I've created some internal variables for our deployer address and our operator address, and then a variable for our service manager. So Forge scripts provide for a setup function, and in our setup function, I'm going to pull in a private key for our deployer and a private key for our operator. And these are just going to be created by our local environment. We're going to be using a command line utility called Anvil, and this runs a EVM on your local machine that you can actually deploy and test contracts with. So these keys will be created once we run that program. And then here I just give them a label. In Foundry, the actual business logic of our script is handled by this run function. And here deploying a contract is as simple as calling this start broadcast, which tells Forge which address to use for deployment. So we're going to use our deployer. And then we're going to basically create a new instance of our service manager and pass in the AVS directory address that we defined above and store that in the variable that we created before. And then we call stop broadcast. So before an operator can register with an AVS, they need to register to EigenLayer itself. So we do this through the delegation manager. And so we need to pull up the live instance on chain of the delegation manager, and we set that through this call right here, passing in the address we defined above. Then we set some operator details using this struct from the interface we pulled in. So we just need the earnings receiver, basically where the operator wants to receive their rewards and earnings. So we pass in the operator address. Delegation approver, we don't need that right now, and we don't need this stake opt-out window blocks either. So we just set those to 0. And again, we call this start broadcast function. And in this case, we're going to be using the operator's wallet to run this transaction. And then we're going to call register as operator with the operator details that we defined and pass this as blank. Then call stop broadcast. Now, finally, we need to register our operator to our AVS in order to be able to respond to tasks. Let's pull in the instance of the AVS directory that's already deployed on chain. Using the address we defined above, we're going to create a salt, which is basically just the concatenation of the block timestamp plus the operator address. And that's going to be a bytes 32, and then an expiration. And this is basically an expiration for the signature. We're going to pass signing that we want to join this AVS as an operator. And the signature is going to be set to expire 1 hour from now. We need to create the message or the hash to sign, and we can use that using the digest hash. I know that's a mouthful, but it's a utility function for creating the hash to sign. And all that takes is the operator address, the address of the service manager or of the AVS that we want to join, the salt, and the expiration. And then we sign this hash using the vm.sign utility function provided by Foundry. And this just takes the private key and the hash that we calculated above. And we need to basically convert the different parts of the signature into a single byte string. So we can just use the abi.encode pact and pass the R, S, and V values together. And that just creates the signature string. And then with this struct that we saw in our contract that we created, we basically construct that using the signature, the salt that we already created before, and the expiration. This is what we're going to pass to our service manager when we register. And again, we call the start broadcast function with the operator as the broadcaster, call our service manager contract, and then register operator to AVS using our operator address and the signature that we just constructed. And that's it for deployment and registering operator to our AVS. Next, we're going to set up a local environment and get these contracts deployed. So we're going to be using Anvil. We're going to set a very specific chain ID, and then we're going to fork the state of mainnet as it is live right now. And this will save us some time, so we don't actually have to deploy by hand all of the EigenLayer core contracts. We can actually play with this network on our local machine as we were actually working with mainnet, which is pretty cool. So we're going to run this command. And as you can see, Anvil has already created a bunch of fake addresses, given it a bunch of ETH, and given you the private keys that you can use to run some tests. So we're going to copy this first private key. I'm going to open a new tab, and then we're going to edit a .env file. We'll set a private key variable to the first private key. We'll copy this second private key, and then we'll paste that into our .env file as the operator private key. Now, don't even try to use these private keys in production or real life. These were generated randomly. These are not meant to be used to store actual funds because other people probably have these private keys as well. So I wouldn't send anything to the addresses associated with these keys at all. We're only going to be using these keys in a local environment, so it's pretty safe to display these on the screen. I have no worries about it because I'm not going to be sending any funds over there. So now in our terminal, we can run this deploy script. So we use the forge script command, call the script we just created, passing the RPC URL, which is localhost at port 8545. This is in reference to the Anvil instance that we just started, and passing the broadcast flag. So let's go ahead and run that. And that ran pretty fast, but you can see 3 different transactions. The first transaction is the deployment of our contract. The second is registering to EigenLayer as an operator, and then registering to our AVS. And we're going to keep track of this contract address for the backend scripts we're going to create next in order for operators to interact with our service. Now, like I said before, I'm not going to show you how to set up Llama, but I'm going to show you that I have Llama set up on my machine and how this actually works. So you call the Llama command and then the run command and then the model you want to use. So in this case, Llama Guard 3, the 1 billion parameter model, and then pass in a prompt. So this model will basically pass a response, safe or unsafe, depending on the prompt you send. And we're just going to pass in a silly prompt. Let's rob a bank and see what it says. You can see it's pretty fast and it passes back unsafe. So this is basically the model has decided that talking about robbing a bank is probably unsafe content. So let's pass in another prompt, Ethereum to the moon, for example. And you can see there's nothing unsafe about this. So it responds with the response of safe. So for our operators stack, we're going to be using TypeScript and Bun. But the great thing about EigenLayer and AVSs is that an operator can run basically any stack that they want as long as they're following the rules of the service that they're operating for. So we're going to create a package.json. I'm going to paste in a few dependencies. We're going to require the types for Bun, env, so we can read our .env file, the Llama library, and Veeam, which makes it very easy to interact with smart contracts. Then in our terminal, we can just run bun install. With everything installed, we can go ahead and create our first script. And we're going to create a script to create a task. At the top of our script, we pull in some dependencies like anything. We're going to pull in this create public client, create wallet client, HTTP, and parse ABI from Veeam, private key to account from Veeam accounts, this Anvil chain definition from the Veeam chains, and then import.env config. And this essentially, by importing this right here, it's going to read in our .env file automatically. Next, we're going to want to make sure that our private key environment variable is set. If not, we just want to throw new error and basically quit the script. Here, we're going to create a simple type for working with tasks. This is going to match the task type that we created in our smart contract, and it's got the same properties, contents, and task created block. Here you can see one of the nice things I like about Veeam. You don't actually have to pull in huge JSON ABIs from your contracts after you compile. You can actually use this human readable ABI format, which basically allows you to define what the function looks like, and then Veeam is able to create an ABI object from that using this parse ABI function. So basically, we've passed in the signature of the create new task function that we want to call, and Veeam will be able to intelligently use that when we actually interact with our contract later on in this script. Here, we're just going to create a function called main that runs all of the business logic in our script. And next, I'm going to define the contract address. This is literally copied from the Anvil screen that we saw before for the contract address that we just deployed for our service manager. And just to note that if you stop Anvil and then restart Anvil with all the same properties, you're going to get the same address every time. So luckily, we don't need to change this whenever we stop and restart Anvil. Next, we're going to create an account using the Veeam private key to account function. And that's just going to take in the private key. And we basically need to cast it as this very specific format that Veeam expects. After that, we create a public client, and this is used for read-only operations. And we're going to use the Anvil chain that we pulled in and define the transport. The transport is basically which protocol do you want to use to interact with your chain. You can use WebSockets. In this case, we're using simple HTTP, and we're calling localhost at port 8545, which is the port that Anvil is running on. Next, we'll create a wallet client, and this is the client that can actually create transactions on chain, so write operations. And of course, we pass the same parameters, Anvil, the URL, and this extra variable right here is the account that is going to be signing transactions when we write them on chain. Then in a try catch block, we're going to first simulate the call to the chain. And this is a good practice when using Veeam. Basically, it saves you from trying to send transactions that are going to fail, revert, and end up spending your gas for no good reason. We pass in the contract address, the ABI that we parsed using parse ABI, the function name, create new task in this case, and then any arguments, and they're passed in an array in the order that they're supposed to be received in the function. So we're just going to pass a content of what a lovely day. Of course, this is most likely going to be determined as safe when passed through the AI LLM later on. And then we pass the account that's going to be sending this, and that's the account.address. Next, if the simulation passes, we're going to take the request return from that and then send that to write contract in the wallet client, and then wait for a hash to be generated. Once we have a hash, we can actually wait for the transaction to be mined using this public client receipt. And once we get the receipt, we can just log the hash and the receipt. And then finally, we can handle any error by just logging it to the console. The very last thing we need to do is actually call this main function that we just defined. So we just can call it right here and then catch any errors that may arise and console log as well. We can go ahead and run this in our terminal using bun run and then the name of the script we just created. And here you can see we got a bunch of stuff back. You can see we got the transaction hash, AF750 is the ending, and then a receipt saying that it was a success. If we go back to Anvil, we can see this AF750 hash right here, and that just shows that the transaction went through. Great, now all we need to do is create the operator script. So let's go ahead and create a file called respondtotask.ts. Again, we import a bunch of dependencies like before, the different clients, the transport, parse ABI, and a few other utilities from Veeam. I'll show you how they're used below. We also import private key to account, the Anvil chain, and also we need to import Llama in order to interact with Llama, which is running on my machine. And again, the .env/config, which reads our .env file. Just as before, we make sure that the private key is set. In this case, we want to use the operator private key. We also create a task type as before. Again, we're going to need an ABI in order to work with our smart contracts. In this case, we want to call the function respondToTask, which has this signature. And then we also want to listen to the new task created event. So we need to add that to our ABI as well. Next, we're going to create a few useful functions for responding to tasks because we're going to have to work with some signatures and hashes. Let's go ahead and create a function called createSignature. This will take the account, the response from our LLM, safe or unsafe, the contents of the string. And right here, we basically recreate the hash the same as we did in the smart contract. And then we create a signature using account.signMessage. And this will take in the raw message or the message hash and return a valid signature string. Next, we'll create a respond-to-task function. This will take in the wallet client, public client, the contract address of our service manager, the account, task, and task index. And these are all going to be called from our main function, which we will define below after all of the boilerplate setup. So the first step in a try catch block, we need to actually call our LLM. So we use the Llama client and the chat method to call our Llama Guard 3 model, pass in a message. If you're familiar with working with OpenAI, you'll know that messages are constructed in a certain way with roles. So in our case, the role is us as a user. We pass in the content of the prompt, and that's going to be the task contents, and then we get the response out. We'll first assume that the message is safe, but if the response text from Llama includes the word unsafe, we can set that to false. Now that we have a response, we can create a signature from that response using the create signature function that we defined above. So we'll pass our account, which is going to come from these arguments up here. The is safe or unsafe, and then the contents of the task. And as is good practice when using Veeam, we're going to simulate our contract call, calling the contract address using the ABI, calling the function respond to task with the arguments task, the index, whether or not it's safe, and our signature. And then we pass in our account address. Then if the simulation passes, we pass on our request to the write contract function in our wallet client. Then with that hash, we wait for a receipt. And then once the transaction is mined, we just go ahead and log to our console that we responded to the task with the hash that was mined. And then we handle any errors. If there's an error, we just log that to the console. Next, let's create the main function that we're going to call. We set our contract address as before, pull in our private key to create the account object, and then create our public and wallet clients. Next, we're going to tell Veeam to watch for new events. And so we can use the public client watch event, give it the contract address, and then tell it which event to look for. So we use this parse ABI item. We're going to pass in the signature of the event again, and that gets passed to this. And then use this on logs callback parameter property, and then wait for new logs. We pull in the arguments from the event. If there are no arguments, then we continue. And then we take the task index, which is basically the ID of the task. We cast that to a number, and then we take the actual task, which is the task struct that we defined above. We log that we've detected a new task, and then we call this respond to task function that we just defined above. And then these lines right here are basically to keep our script running forever until we basically hit Control-C in our terminal. This is telling this script to wait for that Control-C signal, and then it will cleanly shut down. And then down here, we're awaiting a promise that will never come, and that's what keeps the script running forever. Then again, the last step is to call this main function and then catch any errors. So in my terminal, I'm going to open two panes. I'm going to run this respond to task script, and we're starting to watch for new tasks. Then let's run this create task, and you can see that the watch for task script detected a new task, and then ran it through the LLM, responded to the task, and then decided that the content we sent through was safe, so it set it to true. And we can check this transaction hash 4C4F9. If we go to Anvil, we can see the transaction hash 4C4F9. Now let's try this again. I'm going to change the text in my create task script to I want to rob a bank. We'll go ahead and run the create task script again. You can see here the receipt, new task detected, I want to rob a bank. And the LLM has determined that this is not safe content, so it set it to false. And this is the transaction hash 0C2B3. And we can see the hash 0C2B3 has been mined on chain. And that's it. That's how you can create a very bare bones but working AVS on EigenLayer. Now, as I mentioned before, there are a few things missing from this AVS tutorial that you're going to want to take into account when building an AVS in production. One, you're probably going to want to make sure that any operator working with your AVS has a sufficient amount of stake delegated to them. Without this, you're not going to be able to leverage the security guarantees provided by EigenLayer. You're also going to want to set up some sort of reward scheme. This will incentivize operators to actually work with your AVS, as well as incentivize stakers to delegate their stake to operators on your AVS. To find out more about staking, rewards, slashing, etc., check out the EigenLayer documentation, linked in the description down below. If you'd like me to do a more detailed video on those topics, also let me know in the comments below. If you have any other comments or questions, leave them down below. Once again, thanks for watching, and I'll see you in the next video.